Welcome to the underwater edition of Vibrometry Explained. We're going to talk about making measurements through water or through water and glass, let's say in a glass container. So that's the theme. And what I want to do is kind of make the pointers through examples. So for example, in this case, the measurement is on a dental descaler. So number one, you want to use the helium neon laser source, not the Q-Tech, because the Q-Tech uses the infrared laser, which gets absorbed at the water surface. So if you're going through a surface, HeNe is the choice. HeNe is the one you want to use. Secondly, if you are after absolute displacement or absolute amplitude, velocity or displacement, then you need to account for the refractive index of the medium as well. So in this case, water. So when you're measuring through air, you don't need to worry about it because the refractive index of air is 1. But with water, for example, you may want to divide, whatever the output is by the refractive index, example 1.33. For clean distilled water. So that'll give you the absolute amplitude. So if the frequencies are what they are not going to change, but your amplitude does need to be scaled based on the refractive index of the medium. Another example, this one is using one of our single point vibrometers and with a scan set or some scanning mechanism in front of it to make it a single point scanning vibrometer. So continuing with the theme, you want to increase the distance between the surface of water and where your device or your measurement object is sitting, because the more that distance, so you are ensuring that you are focused on the object and you are as much as possible defocused on the surface of water. So if you increase that distance, that definitely helps. And same goes with, kind of goes hand in hand, that if you can make your depth of focus as shallow as possible, you can really, ensure that the light coming back is predominantly from the surface where the beam is focused. So if your depth of field is very shallow, then you are not getting anything or negligible amount of light from any other surface, including the surface of water. So reducing the depth of focus and or increasing the distance between the surface of water and the surface of the device under test. Here's a nice test example from UT Austin showing actually measurements on a tiny fish and what's considered the hearing mechanism or hearing organ of a fish called an otolith, in which in this case, as you can see, we were quite close to the glass water surface. So again, the smallest spot size possible. In this case, that was also critical. And also it helps with the smaller the spot size, the shallower is the depth of focus. In this case, you can see that to reduce the spot diameter and the depth of field, we were using a microscope-based system. And it was not necessarily to see where we were measuring, but mainly to reduce the spot size and reduce the depth of focus. It's also a good idea to do a background measurement. So without excitation, then you know what is coming from the glass. I've also done measurement by actually focusing on the glass itself to see what effect the glass could have on the actual measurement. So if you notice that even when you're focused on the glass, if the effect is negligible, you can rest assured that when you're not focused on the glass, you're going to get good measurements. This picture is also, it's actually a very interesting measurement. This was done on a glass, through water on a air bubble surface. So this was a very challenging measurement, but very successful measurement. But the point I wanted to bring out is, if possible, use glass and not plexiglass. The reason being, plexiglass is more prone to scratches, and what happens is every scratch could result in it could become a source of reflection. So the cleaner, the clearer, the more truly optically transparent the surface is, the better. So glass always works better than plexiglass. And we also noticed that, the clean water obviously works better because it's all about line of sight. If you have stuff and dust and dirt in your water, that could potentially come into the view, into the optical path, and cause noise or spikes in the data. So a lot of it could be cleaned out with good optically sensitive vibrometer and averaging, but you want to try and start with clean water. And in this slide, a couple of more things before we wrap up. Going slightly off angle also helps from the glass. In this case, it was an ultrasonic transducer that was underwater. Going off angle helps because even if there is some light coming from the defocused portion on the glass surface, if you go at an angle, then it further reduces any backscattered light from the glass coming back to the detector. So being defocused plus being at an angle definitely helps a lot. In some very critical applications, we've also done anti-reflective coating on the glass. So you further it. It's all about trying to maximize the signal on the light coming back from your surface of interest, and at the same time minimize any light coming back from any other surface, including glass. So to that end, AR coating on the glass also helps in some critical applications, especially when you are measuring very, very small amplitudes. Let's end the presentation with these questions. 3 questions: measurement on a water droplet, through a water droplet, and measuring in or through oil. The answer to all these questions is yes, absolutely. This can be done. For the first 2 questions, it's all about maintaining and keeping your depth of field as shallow as possible to separate the surfaces. With regard to measurement through oil, it's all about how clean or clear your oil is. The more clear it is, the easier the measurement. So definitely reach out if this is something you're dealing with. We have had some good success measurement through oil. And with that, I want to end this presentation. Thank you so much for your time. And until next time, see you later. Bye-bye.